Okay, now we're going to talk about equilibrium constants. Okay, equilibrium constants are a way we can determine if the reaction favors products or reactants. So if we write our equation for A and B making C and D, where A, B, C, and D are our reactants and products, the chemicals, and smaller case A, B, C, and D are the coefficients or the number of moles of each of those products and reactants. We make an equilibrium constant by putting the products over the reactants, the concentrations of the products over the reactants. So if we look at the box at the bottom, we see that C and D are our products, and we raise them to the exponent that corresponds to these coefficients. So product C and D to C and D exponent, number of moles. Our reactants were A and B, so they're raised to A and B. Okay, that's what K, and the EQ means equilibrium. So it depends on temperature. This is a very important thing. The only thing KEQ really depends on is temperature. So there's temperature. So this is hot water, this is cold water. N2O4 are these little squares, and we'll see there's very few of them in the hot water, and then in the cool water there's lots of them. They're not going to basically react as much. So the equilibrium here favors the reactants a little bit more, and then this one favors the products. So the K depends on the temperature. And I think I mentioned this before, that size of the equilibrium constant indicates whether reactants or products are more common at equilibrium. If it's large, like 10 to the 11th, it will favor mostly product. If it's small, like 10 to the minus 11, it'll be mostly reactant. And if it's somewhere in the middle, you probably have significant amounts of both. So we're looking at ranges between 0.15 to 50. So how can we calculate this? Well, we have to know something about the concentrations of our products and reactants. So if we look at this dinitrogen oxide and nitrogen dioxide, or it should be dinitrogen tetroxide and nitrogen dioxide, we have moles of each of them, and we can write at 10 degrees, so we can write an equilibrium expression. So we basically know what our moles of each are. So we have that many moles per liter. So let's go back to a second. Okay. We know it's liter because it said that in the problem. And we have that for NO2 also. So we don't know our KQ yet. So let's decide how we're going to do that. So we know that's our general formula. We only have one of each type of thing. So we have NO2 is our product, and N2O2 is our reactant. And we make 2 moles of NO2 for every mole of that. That's why this is raised to the second power. All right. If we substitute in then, we'll see that our moles per liter cancel out, and usually we write K with a unitless number. So it's actually a naked number, believe it or not. Okay, so KEQ is a naked number. That's how we solve for it. Products over reactant raised to the coefficient in front of those reactants in the balanced chemical equation. Now we can ask ourselves, does the result make sense? If you raise to the correct power, if you have 2 significant figures, and it's appropriate for an equilibrium mixture that contains significant amounts of both gases. It's somewhere between 0.15 and 50. Now let's try it again. Let's try a sample problem. We have hydrogen gas and a mole of violet iodine vapor. They're in a 1 liter flask, so we have 1 mole of each, and they react at 450 degrees C. At equilibrium, 1.56 moles of colorless hydrogen iodide is present together with some of the reactant gases. So what we know is we started out with 1 mole of each, and we have 1.56 moles of colorless hydrogen iodide. If it went to completion, we would have 2 moles based on the equation. So what we can do is we can use our concentrations of what we know, okay, because 1.56, that will help us to know how many moles that we have left over. All right, so we have our initial values and we have our equilibrium 1.56. So let's see how we can figure this out. So we have x plus x equals 1.56. 2x equals 1.56, so x must be 0.780 moles of H2 and I2 are consumed. And if we had 1 to start with, we would subtract that number from 1. So there's 0.22 moles of each of them left over. So we write the equation and we substitute in the values we just had. So we have 1.56 moles per liter of our products, and we have 0.22 moles per liter of each of our reactants left. We cross out our moles per liters, and we end up getting 5 times 10 to the 1, or 50. So there should still be some of each, but it's on the higher end there. Now what if we want to find concentrations at equilibrium? So here we have bromine chloride making Br2 and Cl2. They say that it's a specific temperature. They don't tell us what it is, but at some temperature, meaning that's constant, we have K. Okay, they say the equilibrium constant is 11.1. So K equals 11.1, which is in our range, saying there must be some of everything there. We know that's in 1 liter, so we can actually, and we allow it to decompose. Then it tells us some information. It says at equilibrium we have 4 moles of Cl2. What are the equilibrium concentrations of Br2 and BrCl? Okay, so if we have 4 moles of Cl2, and 2 makes 1, so that must be 8 to start with. Then this has to be 4 also. Make sense? Because they would have to be the same amount. So if we look at 11.1, so if we think of these as our products, we could say 4 moles times 4 moles and we could say that's over x. Okay, so theoretically, by that, we would have that as our idea. We can't just substitute it in, but we would know that there'd have to be the same amount of these two things because it came from that. Okay? So let's look at it. We have 4 moles. We say we don't know Br2, but we can look at that. So let's go through how to go through this process. So we have 4 moles per liter. There's our equilibrium concentration. Okay. And what we really don't know is the BrCl2. So we know that Br2 has to be 4. So we just solve for it. Okay. So let's look and show. Let me show you what we did. So we had this products over reactant equals KEQ. So let me rewrite that over here. So we had Br2 times Cl2 over BrCl2. Okay? So since these are going to have to be made at the same amount, we know that these numbers have to be the same. But what we did is we arranged it so the unknown is here. And notice it didn't come out to be 8 because that would have been how much we need. This is how much is left over to make that 11.1. Okay? So it's just rearranging. It's a little algebra. Now, the only problem with this is that was our squared value. We have to take the square root. Okay, here's a chance for you to do one of these problems on your own and use Pearson to figure it out. I'm sorry, educating. So we have hydrochloric acid is formed when you have H2 gas and Cl2 gas. We have equilibrium concentrations of HCl and H2Cl2, so we know all the concentrations. All we have to do is figure out the equilibrium constant. So it will be a naked number. Okay, go ahead, try to figure it out. With you in a minute. How'd you do? All right, did you do this? Did you raise the HCl as a product in the numerator to the second power? What about your H2 and Cl2? Did they make sense to be your reactants? They belong on the bottom. Okay, we know all the values. We just plug them in, and there we go. We get an answer of 121. Okay, let's summarize. At chemical equilibrium, both the forward and reverse reactions continue, but their rates are equal. No net change occurs in concentration of reactant components. Stresses upset the equilibrium, so according to Le Chatelier's principle, we need to respond to those stresses. What are those stresses? They can include things like concentration of reactants or products, changes in temperature, and changes in pressure. The size of the equilibrium constant will tell us if the reactants or products are more common at equilibrium. Very large equilibrium constant means it favors the products. Very small favors the reactants. And intermediate means there's significant amounts of both. KEQ expression is shown. Reversible reaction means it can go both ways. Equilibrium is a state of balance where the reaction rate is the same in both directions. So there's no net change in concentration of the reactants and products. The position is where the concentrations of the reactants and products have reached a ratio that is constant. The Chatelier principle, when a stress is applied to the system at dynamic equilibrium will shift in a way to relieve the stress. And KEQ is our equilibrium constant. So that's it for these 3 videos. See you soon. Bye now.